So really, this should have been in blue. You know, I'm not a stickler for much, but a man has to have standards. So there we go. There's our blue. Good morning, good afternoon, good evening, good night, good whatever time it is where you are. It's been a minute since we've done a Math Minute, and that's what I want to do today. Although this one's going to be a little bit different from my other Math Minutes. I'm not so much explaining something as discussing my own, not quite confusion on the matter, but let's call it a lack of clarity. So I saw this tweet the other day from Timothy Gowers. He is going through problems and putting up his process for solving them online. I do that sometimes, but the difference between us is that I'm an 8th grade math teacher and he's a Fields medalist. So he's tackling problems that are a little tougher than I normally tackle. And let's be honest, he's a little better at it than I am. But this particular problem was interesting to me, water break, and I do want to try to solve it at some point. I don't think I'm going to be able to solve it right now, but I did have some initial thoughts that I wanted to talk through. And so let's take a look. The problem is this, first of all. Take integers n, a, b, c, and d, and prove that if you look at n squared and the next consecutive square after that, n plus 1 squared, there cannot be any integers in between those two perfect squares, such that the product of the greatest and the least is equal to the product of the middle two. That is, in this particular case, we're supposed to prove that a times d cannot equal b times c. There are a few thoughts I had about this, and first of all, being an 8th grade math teacher, the first thing I try to do is make this a little bit more concrete. So what are we talking about here? If, for example, you let n equal 1, this isn't even possible, because then your lower boundary would be 1 squared, which is 1. Your upper boundary would be the next perfect square, 2 squared is 4, and there isn't even room between 1 and 4 to have 4 different integers. So in fact, the least we can ever let n be is 2. But if we let n equal 2, we get a sense of what's going on here. That means our lower boundary now is 2 squared, which is 4. Our upper boundary would be 3 squared, which is 9. And there are, in fact, 4 integers between 4 and 9. There are actually exactly 4 integers between 4 and 9. We could let the other integers be 5, 6, 7, and 8. And you do see here that if we take the product 5 times 8, it is not equal to the product 6 times 7. Right? 40 does not equal 42. So at least with our least possible case, where we can even have the space for those integers a, b, c, and d, it turns out that a times d is not equal to b times c. But again, we're not supposed to demonstrate that this just doesn't happen one particular time, or 2 particular times, or even 1,000 particular times. We're supposed to demonstrate that, in fact, no matter what integers you choose between those 2 perfect squares, it can never happen. So again, in this particular case, there wasn't much choice about it at all. A had to be 5, D had to be 8, B had to be 6, C had to be 7, and indeed A times D was not equal to B times C. But you can easily imagine, let's not have n be small, like 2. Let's have n be really large, like 23. In which case, we're now bounded by 23 squared and 24 squared, and there are all sorts of integers between 529 on the low end and 576 on the upper end. Surely we could find some arrangement, some pair of integers in between 529 and 576 such that we could make the product of the outer two equal the product of the inner two. Well, I'm not going to sit here and run through Excel or anything to have it generate a bunch of products and see whether or not that actually happens. If our job is to prove that it's impossible, let's assume it actually is impossible, and we will not be able to find any such pairs of integers that work that way. So to start working my way into the question, I kind of wanted to think about limitations. Why is it that this is happening? So there clearly must be something special about 2 consecutive perfect squares. But what if they're not consecutive? What if we do something like let n equal 1, and so our lower boundary would still be 1 squared, but instead of having our upper boundary be the next perfect square, which in the case of letting n equal 1 we've already seen does not work at all, we don't even have enough room for a, b, c, and d, what if I decide to let that upper boundary be the next perfect square? So in this case, that is going to be 3 squared. Can I find 2 integers that pair up and match the product of another 2 integers between 1 and 9? And the answer is yes, we can, really easily actually. You could let your least number be 3 and your greatest number be 8, and then you could let the other 2 be 4 and 6. And so in this case, A is 3, B is 4, C is 5, D is 8. And indeed, if we take these products, 3 times 8 is equal to 4 times 6, right? 24 does equal 24. So what is it that's going on about the consecutive perfect squares that makes this impossible, when if we just jump one square away, it's no longer impossible? That's the problem, right? That's what we're trying to prove. There must be something that's happening when we restrict our upper and lower boundaries to consecutive perfect squares that makes this kind of relationship impossible. The other restriction we could remove and make this process relatively easy is to get rid of the fact that a, b, c, and d have to be integers. So let's consider something like let n equal 3. And so now we're going to bound ourselves, that sounds a little weird, we're going to bound ourselves between 3 squared and 4 squared, right? So we're looking between 9 and 16. Imagine that we wanted to keep things simple, and so we just say, all right, let's have a be the next integer up, 10, and let's have d be the other integer down from our upper boundary, 15. That means that our product, a times d, in this case is just 10 times 15, which is 150. Let's again keep things simple. For b, we'll just pick the next integer up after that, which would be 11. If we were to set this equal to 11 times something, right, some c in particular, again, if we remove the fact that a, b, c, and d have to be integers, this is trivial. All we have to do is divide by 11, and in that case, c ends up equaling, what, 13 and 7/11, so 13.63, repeating on and on forever. And so that's really easy. We can pick any 3 integers we want using this system, having removed the restriction that a, b, c, and d have to be integers, and it's trivial. So again, I go back to, what is it about those 2 restrictions, that the numbers we're looking at be integers, and that they have to be between 2 perfect squares, bounded between 2 perfect squares? What is it about those restrictions that make this so difficult, that make it actually impossible to make the product a times b equal to the product b times c? I think it's useful, as I discuss this next thing, the thing that actually piqued my interest in this question, to kind of understand that there are 3 different levels of numbers going on in this question. We've been picking relatively small n, like the example we used for showing that there's at least one case where it doesn't work, is we said let n equal 2, which of course means that n plus 1 is 3. But then n and n plus 1 aren't themselves our boundaries. There's one level up from there. It's the squares of n and n plus 1 that form our boundaries. And so that's the next level up, right? 2 squared actually makes 4. 3 squared actually makes 9. And so we start out on one level looking at relatively small numbers, 2 and 3. And then we jump up a level to get our boundaries, and these numbers are going to be roughly comparable. They're going to be in the range of a, b, c, and d. Again, when we chose the example, there were only one possible a, b, c, and d arrangement, and that was just to count your consecutive integers between 4 and 9. So on the one level, we've got n and n plus 1. The numbers that we square to generate our boundaries. And then on the next level up, we've got the boundaries themselves and a, b, c, d, the integers that live between those boundaries. But then there's actually a third level of numbers, and this is where I find the problem to be really interesting. That third level, let's go ahead and start labeling. Let's call a times d j, and then let's call b times c k. And so what we're really proving is that j, for some reason, cannot equal k. Well, j and k are on a whole other level from the numbers that we're looking at. And again, if we go back to the particular example we saw earlier, if the initial numbers are something like 2 and 3, the boundaries and all of the integers we care about are at the next level up, 4 and 5 and 6 and 7 and 8 and 9, and then the products themselves are on a whole other level. 40 and 42 are much larger than our boundaries. Of course, what's going on here, the reason for this, is that you can think of j and k as being bounded not by 2 consecutive perfect squares, but 2 consecutive perfect quartics, right? Is that what it's called? Tesseracts, 4th powers. It's going to have to be the case that whatever j and k are, they are themselves bounded by 16 at the low end and, oh my gosh, 81 at the high end. And so you can see even choosing really small n's on this third level up gives us relatively large boundaries. J and K can be anything between 16 and 81. And again, our job is to show that they cannot actually be equal to each other. There's no such J, no such product of A times D that's going to end up being equal to K. Anyway, it was at this level of the problem that I thought it started to get interesting, because there's this funny thing that happens when you factor. And actually, now that I think about it, the last couple math minutes were about factoring, so maybe this is why this problem kind of stuck out to me and why this has been on my mind. If you factor a number, like say 48. Usually the process that you go through is you start with the most obvious pair of factors, which is that every number is its own factor. Every number is itself times 1, right? So that's 1 times 48. And then usually, at least when you teach 8th grade math, what you do next is you just start to count up. So after 1, the next factor of 48 is 2, and it happens to be 2 times 24. And then after 2, the next factor up is 3, happens to be 3 times 16. And so you can see on the left side of the table, the numbers are getting larger, whereas on the right side of the table, the numbers are getting smaller. This is an inverse variation kind of idea. In fact, if we were to graph these ordered pairs, you would see a rational curve in quadrant 1, where we're keeping our product constant, but we're just changing what the numbers are that make up that product. After 4, we get to the first number that's not actually a factor of 48. 5 does not go into 48 evenly. Again, we can definitely come up with some kind of fractional or decimal numbers that multiply up to 48, but there's no 5 times some integer that makes 48. Instead, after that, we get to 6 and 8, and then we know we can stop. And the reason we know that we can stop is you always want to be thinking of roughly the square root of the number that you're factoring. 48, of course, is not a perfect square, but it's really close to a perfect square. It's close to 49, and the square root of 49 is 7. So the square root of 48 is a little bit smaller than 7. What that tells me is that on my left side of the table, as soon as I get to 7, I know that I'm done. Because now there's no larger number that's going to end up being a factor of 48 that I won't have already seen on the right side of the table. I don't need to test out 7 or 9 or 11 right now. I don't know why I skipped 10, because I haven't already seen them on the right side of my table. And so it's that relationship between this number up here, these pairs of factors, and then the square root down here that made me think of the initial problem that Timothy Gowers went over. You can think of the root 48, that kind of boundary where you can stop factoring, as being related to the n and the n plus 1. You can think of these numbers in the middle, the actual factors, which obviously in this case do equal each other because I was factoring the same number, as being your a's, b's, c's, and d's. So it's like a is 3, b is 16, no, that's not right, b is 4, c is 12, D is 16 on our factoring chart. And then up here at the top level, your 48, this would be the number that's comparable to J and K. And what we're saying is that there's going to be some set of factors for some number J and some number K, such that you can't arrange those factors into this kind of order, have them equal the same product where J and K are equal, and yet also down here at this level, have these be bound between two perfect squares, two consecutive perfect squares. For some reason, it doesn't work. But that's as far as I've been able to get so far. I don't know yet the reason that it doesn't work. I don't understand the reason quite yet that it's really easy to do this process if you don't restrict A, B, C, and D to integers, or that it's really easy to do this process if you don't restrict your boundaries to consecutive perfect squares. So, if you were going to teach me how to do this, what would your next step be? What is it that I'm missing? Is there a spurious connection that I'm making? Comment down below. Please let me know. Kind of a weird math minute. I don't normally do this, but this is my cry for help to you, the wonderful mathematical audience out there on YouTube. I hope that that was kind of an enjoyable explication of just how to begin thinking about a problem, at least when you're not a Fields medalist. I will see you all the next time.